Okay, so talking about energy, and again, hopefully some of this is not new information for you that you've learned it in a previous science course. So, uh, but we want to hit the highlights because it's important for understanding the new information. So really, there's two types of energy. There's potential energy, and then there's kinetic energy. Okay, and when you're talking about chemistry and at the molecular level, how do we distinguish the two types of energy? Well, the potential energy in chemistry at the molecular level really is the chemical bonds. Okay, so in general, potential energy is an energy that's there because of the position of something. Like, if you're higher up, you have more potential energy. Well, in chemistry, the position of the atoms, okay, and the identity of the atoms determine the potential energy of the chemical bond that connects them together. So that's the key, is that when we're talking about potential energy in chemistry, we're talking about the chemical bonds. That's kind of the bottom line of it. So for example, here's a bunch of chemical bonds. Like if you have a carbon-carbon single bond, there's that much potential energy there in that bond, 347 kilojoules per mole. So you don't have to memorize these numbers or anything. They're just meant to show you that, there are energies associated with those chemical bonds. And we haven't really talked a whole lot about chemical bonds yet. We just know there are ionic bonds and there's covalent bonds. We will get into that a lot more later in the course. Okay, now kinetic energy is something that's a little bit more intuitive because we deal with this all the time on a day-to-day basis. And that's energy of movement, right? How fast something is going. Something has more energy, the faster it's going. But that's not the only factor, as you'll see. So again, talking about the molecular level, the kinetic energy is just related to the mass of that thing that's moving, like that atom or that molecule, and how fast it's moving, okay? And the equation is this right here. So kinetic energy is 1/2 the mass times the speed squared. Now, in chemistry, what we usually use to indicate the kinetic energy is temperature, because temperature is taken to be an indicator of the average kinetic energy of a system. Okay, temperature is the indicator, the average kinetic energy of a system. So again, at the molecular level, as we increase the temperature, then what we're doing is we're causing all those molecules or atoms to move faster. So as we increase temperature, we increase molecular motion, also known as the speed, right? And so therefore we increase the kinetic energy of that sample of molecules or atoms or whatever it might be. But let's say that we have the same temperature, which implies we have the same kinetic energy. If the mass is lower, if that's what this down arrow M is meant to represent, if we decrease the mass, or if we have a smaller mass, then the speed goes up, because so things are at the same temperature, that means they have the same average kinetic energy. But if things don't have the same mass, then they're going to travel at different speeds. And so that's what this illustration is meant to show you. So what we're going to do is we're going to just assume that we're going to flick these two balls with the same amount of energy, if a person could actually control that. And we'll say that this one is like a ping pong ball, and we'll say that this is like a billiard ball, like a 8-ball or something like that. Okay, so we're going to try and apply the same energy. Okay, so you can see from the animation there that if I apply the same energy to both those, they don't travel at the same speed. Okay, so same energy, but this one had a smaller amount of mass, so it moved a lot faster. So if mass goes down, speed goes up. The billiard ball, even though I applied the same amount of energy, it just traveled a lot slower. Okay, right, that's the idea with kinetic energy at the molecular level. Okay, so here it is, kind of in a more graphical form, what I just said. So light things like H2, remember that it would have a molar mass of 2 grams per mole, versus something like krypton, which is a noble gas that's pretty far down on the periodic table. It's got an average atomic mass of about 83.798. So this is much heavier. Krypton is much heavier, right? So if we apply the same energy or the same temperature, okay, heavy gases like the krypton and the chlorine, which has a molar mass of 70.9, they're going to move at slower speeds. That's what this x-axis is representing, speed, okay, average speed. Or pardon me, no, not average speed, just speed. Okay, so they're going to travel at slower speeds than the light gases like the helium and the hydrogen. Okay, so that's just another way to illustrate what we showed you on the previous slide. But another thing that you should notice that is very important with this particular graph is that it's not like every krypton atom has the exact same speed. There's a distribution. Some of them are growing pretty slow, but then most of them have this speed right here, but then even, some have faster speeds. Okay, and the same thing with the helium. So helium, some of them have really slow speeds, but the most popular speed is, is right there. But then even some of those helium atoms have faster speeds. So that's the idea, is that when you have a certain temperature, like the temperature might be constant at a given value, like 298 Kelvin. That doesn't mean that all of the atoms, all of the molecules are traveling at the same speed. There is a distribution of speed. And so that's part of the reason why we say that temperature is an indicator of average kinetic energy, because they're not all going at the same speed. Okay, so it's like an indicator of the average speed because there's the distribution. So here's just a little chart. This one is not necessarily in your notes, but it's got some important ideas on it. That this chapter 5 in the text is focusing on energy. And there are lots of different types of energies. There's kinetic energy and potential energy, which we already mentioned. But then there's different subtypes of each. There's chemical potential energy, there's gravitational potential energy, and so forth. And then the same thing with kinetic energy. So what we're going to focus on in this particular chapter is we're going to focus on thermal energy, which is a type of kinetic energy. Okay, and that's associated with the motion of the particles. Okay, it's kinetic, so it's related to motion, and it's thermal because it's indicated by the temperature. Okay, so thermal kinetic energy is what we're really going to focus on in this chapter. Okay, so a little bit more terminology. Anytime you start a new chapter, you got terms to learn.
Are you mental?
So here's one of them, and that is a thermochemical equation. So as you can see there, a chemical equation that includes energy as a reactant or product. Okay, so that's the distinction. We've already learned about chemical equations. They have the reactants, they have the products, they have the reaction arrow, and they have all the different phases like solid, liquid, gas, aqueous. But now what we're going to do is sometimes, this doesn't happen all the time, but sometimes it may be helpful to show which side energy is on in the chemical reaction equation. So for example, if hydrogen gas, if 2 moles of hydrogen react with 1 mole of oxygen, it generates 2 moles of water and energy. And so if I were to write the thermochemical equation, I would just include energy there in the reaction equation.
You're a bunch of bloody magicians.
Okay, now it's another term. So thermal equilibrium. So that's where essentially you've reached a point where the temperature is uniform. Because what we're going to see in the next slide is that really energy is going to flow from one object to another until it reaches thermal equilibrium. And the way you know you've reached thermal equilibrium is when the temperature of the 2 objects involved is the same, it's uniform. So a condition in which temperature is uniform throughout a material and no energy flows from one point to another. Okay? Okay, so how does energy flow? Well, first of all, we give it a word and a symbol. So that is heat. If you ever really thought about what heat is really just energy flow from one object to another, or from one area to another. And we symbolize that in chemistry as a lowercase q. Okay, and so it is just it's an amount of energy. It is the thermal energy that's transferred between objects because of a difference in their temperatures. That's the reason why. The reason why energy flows from one object to another, or from one area of a substance into another, is because there's a difference in temperature there. And so you got 2 little illustrations of this. We'll start with the one over here on the right. So I have these 2 blocks. One of them's at 50 degrees, one of them's at 10 degrees. And if I bring them together, have them touch, then the energy is going to flow from the hotter object to the cooler object, and it will stop when the 2 temperatures become the same. Okay, and then you got this animation over here, which illustrates the same thing, but just a little bit more interesting. Take this white hot ball of metal, you drop it on a big block of ice, and it will transfer its energy and cool off until that metal ball stops somewhere inside the block of ice, because it has reached the same temperature as its surroundings, as that surrounding ice, or water perhaps. Okay, so that's the idea with heat. So heat is one way to move energy from one object to another, but another way to do that is with work, okay? And work we're going to define as a way to transfer energy that moves an object through a given distance. So it's a form of energy, and it's the energy required to move an object through a given distance. And you would learn it in physics as work equals the force that's being applied times the distance that you move the object, okay? Well, this is chemistry, it's not physics. So when we talk about work, we're going to focus on the work that a gas would do. So typically something like a gas, because it's expanding or whatever, moving a piston, a gas pushing something, or stretching a balloon, something like that. So work in chemical reactions is always associated with a gas. Usually involves producing a gas that can push something like a piston, or the stretch a balloon or something like that. Okay. All right. So units of energy. Maybe should have started with this, but I think it's okay here too. But
Boring.
there are a couple units of energy that you'll see in chemistry. One of them is the calorie, okay? And so it is the amount of heat necessary to raise the temperature of 1 gram of water by 1 degree Celsius. That's its definition. Now, interestingly, the calories that you see on like food packages, like for example, if you eat a candy bar that's 240 calories, that's actually it would be a kilocalorie, but they don't bother to write it that way, because in food, 1 calorie is actually 1,000 calories as we have defined it here. Okay. Now, the one that's most often used in chemistry, and I'll tell you what, in our, the problems that we're going to do and things like that, we're always going to answer the questions with joules. And so this is the typical unit in chemistry that we use for energy. It is the standard international unit. But there's a conversion factor here. So 1 calorie that we just defined up here is equal to 4.184 joules.
Wow.
Okay, so energy, whether you're talking about heat that's being transferred or work that's being done, it's going to have the same units. They're both units of energy, and we'll, as I said, usually use units of joules. Okay, so now some more terminology, but these two terms that we're getting ready to define, or these next three terms, are really important for grasping this chapter. So first of all, we want to define what we mean by the system. So that's just the part of the universe. I know that's pretty aggressive and perhaps arrogant idea, but so we picked this one thing in the whole universe that we're going to study, but that's how we define it. So it's the part of the universe that is the focus of a thermochemical study. So for example, let's say I'm studying the rate at which a block of ice melts, or how a piece of aluminum cools off, or, et cetera, anything like that. But in chemistry, of course, a lot of times what we're focusing on is a chemical reaction. So that would be our system. The chemical reaction itself would be the system, the thing that we're actually studying. We're studying how the energy changes in a block of ice, a piece of aluminum, or in a chemical reaction. Okay, so you might be thinking, well, duh. Okay, well, it's important to distinguish that from the other things that are present. And so we do that with this term called,
Excuse me?
the surroundings, okay? And the surroundings is, we're just going to define as everything else except the system, okay? So everything in the universe that is not part of the system. All right, that is what we mean by the surroundings. Now, most of the time, practically speaking, that's just going to be what's very, very close. So for example, if we're studying a chemical reaction, it might just be the volume of water that the chemical reaction is occurring in, or a piece of aluminum. Well, that could just be the surroundings of that piece of aluminum. Could just be, again, the cup of water that I sink that aluminum down into, or something like that. So again, it's just to be technically correct, we say it's everything except the system. But practically speaking, it's just really the other stuff that's very, very nearby. Okay, so like a beaker or a water bath, the countertop, the air in the room, just everything else but the system. That's what we mean by surroundings. Okay, so another thing to understand is the relationship between the two. So that's what we call the universe. The universe, hey, in chemistry, it's just the thing that we're studying, and everything else. It's just system plus the surroundings. And you understand why we make a big deal about that in just a little bit. The next slide. But that's what we mean in chemistry by the universe. It's just the system plus the surroundings. Okay? Okay, so why is that important? Well, because a lot of times what we want to know is the direction of heat flow, or things like that. And so we have to, first of all, identify whether it's going into or out of the system. That's the key for chemistry, for this chapter, for the purpose of chemistry. We want to know, is that heat flowing into the system or out of the system? And so when something is exothermic, that means that energy is flowing out of the system into the surroundings. Okay, so exothermic processes are those where energy flows out of the system and goes into the surroundings. And the sign convention here is when we calculate a value for heat, for Q, right? Remember, Q just is the symbol we use for heat. That number is going to be less than 0. So exothermic, negative numbers. Exothermic, negative numbers. Keep that in mind. So here's a picture that illustrates what I'm talking about. So let's say that I have a vapor, something that's in the gaseous phase. And if that vapor condenses into a liquid, remember that liquids have less kinetic energy than gases do. That's something we learned on like day 2, lesson 2 of week 1. Liquids have less kinetic energy than gases. So in order for this gaseous molecules or atoms to become liquid, they have to give up energy. They have to release energy. And so in order for that process to occur, in order for condensation to occur, that system, that gas, that vapor, releases energy into its surroundings. Okay, so it moves energy from the system into the surroundings, and that's called exothermic. Okay, well, the opposite is endothermic. Okay, that's where energy flows into the system from the surroundings, and the values are going to be positive Qs. Okay, so, and this one's a little bit more intuitive because again, we deal with this stuff all the time. If I want to boil water, for example, I start with liquid water, and if I want to turn that into a gas, steam, then what do I have to do? I have to add heat to it. Well, where's that heat coming from? It's not, spontaneously developing in the system. It has to come from the surroundings. So the surroundings are going to give energy to the system, and that's going to give all those atoms and molecules more energy. And so it turns into, eventually it would turn into a vapor, and we call that endothermic. So I don't know if you have this exact diagram in your handout, but you have something similar if you don't have this. And you may, and by the way, in your handout, there may be some information that's in this diagram that's not in your handout. So look carefully and see if you have to write anything onto it. I can't remember. But it's a nice little diagram that shows what we mean and the sign conventions when we talk about how energy flows in the system, in the system and in the surroundings. So in terms of heat, if heat is being absorbed by the system, if heat's coming from the surroundings and going into the system, then that's going to be an endothermic process, and your Q is going to be positive. If the system is releasing energy into the surroundings, okay, that's exothermic, and that means you're going to have negative values of Q. All right, well, what about work? We talked a little bit about work, but now we want to get back to that. So let's say that we have energy being exchanged between the system and the surroundings in the form of work. So not in the form of heat, but we're exchanging energy between systems and surroundings in the form of work. Well, so if the system is doing work on the surroundings, so we have work being done by the system to the surroundings, that is going to be a negative value for work. It's in terms of the amount of energy, it's like a release of energy from the systems into the surroundings. Okay, well, just the opposite is true. If the system is having work done on it by the surroundings, then that means that the value of W, the energy, is going to be a positive amount of energy. So it's kind of just like heat, that if the system is releasing energy, but in the form of work, it's a negative value. But if the system is gaining energy, but in the form of work, it's a positive value. Okay. All right. So now we can talk about the total change in energy, or change in total energy. So there's a couple of different ways to symbolize this. The way that I do it, and the way that CHEM01 does it, and the way that a lot of textbooks do it is with delta E. But actually in your textbooks, the OpenStax textbook, you'll see that it's symbolized with a delta U. And in my previous life as a chemistry professor at the Naval Academy, we use delta U also. So it doesn't really matter. Just it's understanding what you're dealing with, really. But for our purposes, I'm going to continue to use delta E. Okay. So how do we quantify that total change in energy? Well, I know it's related to the amount of heat that's exchanged and the amount of work that's done. Okay, so here's the equation. Okay, the change in energy, the change in total energy is equal to Q plus W. Now, this equation is on your equation sheet. You just need to know when to use it and how to use it. And I'll tell you, the big thing to know with this equation is the sign conventions. Is Q positive or negative? Is W positive or negative? As you'll see in the example that we'll do in just a second. Okay, so here it is. So in this example, we want to calculate the delta E, the total change in energy of a system. So the delta E of a system that releases 12.4 joules of heat and does 4.2 joules of work on the surroundings is blank. Okay, So we're going to start with this equation, right? The total change in energy is Q plus W. And so as I said, it really is just a matter of just deciding if this is a negative 12.4 or a positive 12.4. And is this a negative 4.2 or a positive 4.2? Okay, so let's kind of think it through. So we're saying that the energy the system releases, that's the key word, releases 12.4 joules of heat. So we have the system and it's releasing, okay, heat is being released by the system, 12.4 joules. So that means it needs to be less than 0, negative number. So that right here, that's going to be a negative 12.4. And it does 4.2 joules of work on the surroundings. So once again, we have the system, and that system is doing work on the surroundings. So this is work done by the system. So once again, that means a negative value. W is less than 0. So this also needs to be a negative 4.2. So negative 12.4, negative 4.2, okay? Negative because it's released, negative because it's done by the system. So now I just plug both those numbers into the equation, and voila, there's your answer. So it's a negative 16.6 joules. Okay, so like I said, that's the real, skill that you need to develop for this kind of question, is just deciding if the numbers that you're given should be used as positive values or negative values in this equation. And all has to do with your understanding of this idea, this diagram right here. All right, so now we want to tell you exactly how to calculate a value for Q. And so we're going to do that along with this discussion of this thing called specific heat. And it's symbolized with a lowercase c with a subscript s, or in many times you will see it just as a lowercase c, okay? And by the way, this is going to be one instance where in chemistry we reuse the same unknown symbols all the time. Like later we're going to see that C stands for the speed of light, and we've already used N to represent the number of moles. Well, we're going to see later in the course how N can represent the principal quantum number and things like that. So my little sidebar message here is just get used to the same letter being represented, is different things in chemistry. It's just kind of, you have to look at the context in which the symbol is used. So in the context of thermochemistry, you see a lowercase c. What we're talking about here is the specific heat. So what is the specific heat? Well, that's defined as the quantity of energy that's required to raise the temperature of 1 gram of the substance by 1 degree Celsius. Now, we already saw this earlier when we defined what a calorie is. A calorie is the amount of energy that's required to raise 1 gram of water by 1 degree Celsius. So this is like just, it's like a calorie, but for any particular material. You can have a specific heat for any material. And the specific heat for liquid water is 4.184 joules, right? Okay, so a quantity of energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. And we will use it in the context of this equation right here. So again, you may have learned this equation in like a high school course or something like that. You may have heard it called MCAT, right? So Q equals MC delta T. That's the way that I say it, but because the delta looks kind of like an A lot of teachers will say MCAT. Okay, so, but again, this equation is on your equation sheet. You don't really need to memorize it. Just need to know when to use it, how to use it. So that amount of heat, that Q that we want to know something about, is calculated by knowing the mass, by knowing the specific heat, and by knowing the change in temperature, delta T, okay? And its units are going to be an amount of joules, an amount of energy per gram per degree Celsius. So the quantity of energy required to raise the temperature of 1 gram per gram of a substance by 1 degree Celsius per degree Celsius, okay? So energy per gram per degree Celsius. Units are always very informative, okay? Units will always help you out in chemistry. That's why I think it's best to, when you're doing calculations, to fully write out your units. Okay, so let's do an example calculation with this equation. So how much energy is required to bring a typical bottle of water, 500 grams, from 20 degrees Celsius to its boiling temperature? And we're given the specific heat for water, 4.184 joules per gram degree Celsius. By the way, you'll never need to memorize a specific heat. You might have to calculate it, but if you need it to do the calculation, it will be given to you. Okay, so you know what? I want to do this the old-fashioned way, and then I'll show it to you on the screen. Okay. Okay, so again, what we're going to start with is this equation. So Q equals the mass times the specific heat times the delta T. Okay, and the mass we're given is 500 grams. Okay, and the specific heat is 4.184 joules per gram per degree Celsius. Okay, and the delta T is important I want to talk about this a little bit because it's always final minus initial. So delta T is always T final minus T initial. Okay, keep that in mind. And so if we're boiling water, the final temperature is going to be 100 degrees Celsius, and we're told the initial temperature is 20 degrees Celsius. So that, has an amount of 80 degrees Celsius. So that's where that comes from. But this is kind of the most important thing because this will help you get the sign correct. Remember, we said that the sign on this cue is important. If it's negative, it has one meaning. If it's positive, it has a different meaning. Well, the way in which you get the correct sign on cue is you do this part of the calculation correctly. Okay, always final temperature minus initial temperature. Okay, so now I'm going to erase that, and we'll do it with PowerPoint to let it finish up. All right, and so the other thing that I'll point out is when you calculate that, you get 167,360 joules, right? Now, that's, why write it with that many digits when we can just use the metric system and use a smaller number? Okay, so in energy, in thermochemistry, a lot of times we'll talk about, instead of joules, we'll talk about kilojoules. Okay, so this would be 167 kilojoules. So we want to talk now about this thing called the first law of thermodynamics. And another name for it is the law of conservation of energy. And, last week we talked about that thing called the law of conservation of mass. Mass is conserved, the number of atoms are conserved. Well, turns out that energy is the same. You always will have conservation of energy. And that's the first law of thermodynamics. So energy can be neither created nor destroyed. It just has to be accounted for.
Hey, this is great, man.
No, you can just convert energy from one type to another. So energy can be converted from one form to another, as is illustrated here in the picture. And I think you have this picture in your handout. So remember that, look at this, physics kind of example first, and then we'll talk about the chemistry type example. So, it's summertime, and we'll wish we could go to the water parks, but with the, the lockdowns that probably aren't open anywhere. But anyway, so if you go to the top, you don't want to see me in a water park.
Hey, this is great, man.
Anyway, I'm an old fart. So I'm the type of person that keeps people away from water parks because, why would I want to see that? Anyway, so let's say that I was at the top of this water slide, scaring people away with my pale white belly. I would have a lot of potential energy at the top of the water slide, right? Because of my position, because of the height. And gravity. Gravity wants to pull me towards the center of the earth. So right now I have defied gravity and I've climbed up the stairs and I'm at the top of the water slide. So I have a lot of potential energy. But if I get on the water slide, that potential energy will convert to kinetic energy as I slide down because I'll speed up, right? I start off, at rest, going 0 miles per hour. But I slide down the slide and so I get faster and faster. So my potential energy is converted into kinetic energy. All right, so that's what we mean by energy can be converted from one form to another. Now, in terms of chemistry, think about like how your body uses nutrition. So a sugar molecule, which is kind of the base nutritional molecule, all the carbohydrates and things that you consume essentially get broken down into sugars because that's what your cells can use to generate energy. And so they take the bond. Remember we said at the beginning that potential energy is bound up in the chemical bonds. So all that potential energy in those chemical bonds is utilized, and through this chemical reaction, we break some of those bonds and convert these products, and then we get energy out of that. So again, this is just to show you that, all that energy still has to be accounted for. It's still there, but it's not in the form of potential. Now it's in the form of kinetic. The energy, all that energy is still there, but now some of it's been released to the cells to heat up your body and to do work. By the way, I don't, again, sidebar, I guess I'm full of sidebars this morning, but the average recommended calorie amount per person is like 2,000. I think if I remember right, 1,400 of those calories, most of it, definitely a majority of it, goes into just maintaining your body temperature at 98.6. That's what it's for. Okay, it's not to do any sort of movement or building new tissue or anything like that. The majority of the energy that comes from the food is just to maintain your body temperature. All right, so moving on. So here's the deal. So when we say conservation of energy, what we really mean is that you have to be able to account for that energy transfer between the system and the surroundings. So energy gained or lost by a system must be equal to the energy lost or gained by the surroundings. Okay, it is totally conserved. Now, the consequence of that in terms of math, in terms of equations and things like that is right there, that the change in energy of the system is equal to the negative of the change in energy of the surroundings. So this is just sort of a way to represent the first law of thermodynamics as an equation. Now remember that delta E is Q plus W, and in chemistry, most of the reactions that we're going to be concerned with, most of the processes that we're going to be concerned with, there's no work that's involved, there's no W. So we can also say this, that if delta E of the system is equal to the negative, the delta E of the surroundings, then the Q of the system is equal to the negative Q of the surroundings when no work is done. And again, in this course, that's pretty much all the time. You know, a very challenging question might involve some work as well, but we're not going to get into that. Okay, and we just learned, and keep in your mind that we just learned an equation to calculate Q. All right, so before we start calculating things, there's one other concept I need to introduce, and that's the concept of a calorimeter. So it's just a device that's used to measure that transfer of heat, the absorption or the release of heat by a physical or chemical process. And the deal is that that calorimeter is going to function as the surroundings. That's what it's there to be. Okay, and it's usually because it's well insulated. Because the calorimeter is typically very well insulated, we can just say that the calorimeter functions as everything else in the universe except the system.
See, Billy Idol gets it. I don't know why she doesn't get it.
Okay, so taking where we left off in the previous slide, if the Q of the system is equal to the negative of the Q of the surroundings, since this functions as the surroundings, I can also say that the Q of the system is equal to the negative of the Q of the calorimeter. That CAL is meant to abbreviate calorimeter, negative Q calorimeter. All right, to be even more specific about it is this thing called the coffee cup calorimeter, because for general chemistry purposes, it works pretty well. And all it is it's a coffee cup, and you'll typically have water in it, okay? And you might have a stirrer in it. That's not even a necessary component, because you could just pick it up and swirl it to stir it, right? But the other key piece of equipment in this calorimeter is this thermometer, because what you're going to monitor is the temperature change of the water in that coffee cup. That's the idea. You do something in this water in the coffee cup, and you see how the temperature changes. And the water in the coffee cup is considered to be the surroundings, the calorimeter. Okay, so the Q of the calorimeter is calculated knowing the mass and the change in temperature of the water. So a lot of times they won't even put subscript CAL. They'll just, you'll see it represented as just subscript H2O, because effectively it's the same thing. Whatever happens in the water is what we say is happening in the calorimeter as a whole. Okay, so the Q of the calorimeter is calculated by the mass of the water times the specific heat of water times the change in temperature of the water. Okay, so here is an example problem. So let's say you're analyzing samples of an unknown alloy retrieved from UFO wreckage, and you heat the 10-gram piece of metal to 100 degrees Celsius and then place it in a coffee cup calorimeter filled with 100 grams of water. The temperature of the water initially at 20 degrees Celsius rises until thermal equilibrium is reached at 34 degrees Celsius. Question is, what is the specific heat capacity of the alloy based on this result? And the specific heat of water is given to be 4.184 joules per gram per degree Celsius. Okay. And probably don't remember Okay. So this is what we're going to do. We're going to utilize the law of conservation of energy, the first law of thermodynamics, and we're going to say, okay, well, I can calculate what's going on in the water to determine something about the alloy. So the heat transferred to the calorimeter is going to be equal to the negative of the heat transferred from the alloy. Okay, and so the first thing I got to calculate is that Q subscript CAL, the heat that's transferred to the calorimeter. And I can do that because I monitor the change in temperature, I'm given the specific heat capacity, and I know the mass. Okay, so now I'll advance the slide and I'll go through this calculation with the pen here. Okay, so this is kind of where we left off. Okay, so I believe that we had 100 grams of water. Okay, so that's our mass, and the specific heat of water is 4.184 joules per gram per degrees Celsius. Okay, and we went from 20 degrees to 34 degrees. So the final temperature was 34.0 degrees Celsius, and we were originally at 20 degrees Celsius. Okay, so that's going to give me, you know, a certain number of joules from that, and I'll just do that calculation real quick, and you guys can do it along with me. So 100 times 4.184 times, open up parentheses, 34 minus 20, close parentheses. So I get 5,857.6. So 5,857.6 joules. Okay. So if that's true, then what I can say then is that the Q of the alloy is equal to negative 5,857.6 joules. And that's because of the law of conservation of energy. If this is the Q of the water, then the Q of the alloy, that, you know, this is what caused the increase in temperature of the water. It transferred the alloy, the metal, transferred heat to the water. So that would be the negative, but the same magnitude. Okay. And so then what I'm going to do is I'm going to say, okay, well, you know, Q of the alloy is equal to mass of the alloy times the specific heat capacity of the alloy times the delta T of the alloy. Okay, and so I can just substitute in the numbers now. Negative 5,857.6 joules equals the mass of the alloy, and it was 10 grams. Okay, and the specific heat capacity of the alloy is what I'm trying to solve for. And then the delta T, well, it was at, you know what, I don't even remember what temperature, probably 100, but what I'll do is I'll let PowerPoint take it over from there. So it went down to whatever that initial temperature was, it went down to 34.0 degrees Celsius, okay? And so the idea here, you can see, and I'll let PowerPoint kind of take over, is we're gonna solve for that unknown. I just couldn't remember the final temperature. So I'll let PowerPoint write that in for me and finish up the calculation. Okay, so we'll change back to that. Bam. Okay. So all this you've already seen. I guess I rounded. Yep. Okay, so the alloy is just the negative of that. And that's equal to its own MC delta T. So I plug it in. And oh, 100, okay. So you remember when I said that getting the you know, it's always final minus initial. So this illustrates why that's so important, because you can see 34 minus 100 is going to be a negative number. Well, I've got a negative here, so the two negatives will cancel, and that needs to happen because you can't have a negative specific heat. The specific heat capacity is always going to be a positive value. But if I had not, you know, arranged those temperatures correctly, I would end up with a negative value for the specific heat capacity. Okay, so you rearrange and you solve for the specific heat capacity of that alloy.
It is over. Done.
And you get 8.88 joules per gram per degree Celsius. It's done exactly the same way that I did the example. So you're going to use what's happening in the water to determine a property of the alloy. And so the first thing to do is calculate the amount of heat that's transferred to the calorimeter, knowing the mass of the water, the specific heat of water, and the change in temperature of the water. Okay, so you plug in those numbers, 100 grams, 4.184. In this case, it went from 45 was the final temperature. The initial temperature of the water was 20. So you get 10,460 joules. So due to the law of conservation of energy, the heat that's transferred from the alloy is the negative of the heat that's transferred into the calorimeter. So use the same number just with a different sign. And now we're going to use that number as Q and calculate the specific heat. So we're going to take this number, substitute it here, and we're going to rearrange and solve for the specific heat. Okay. And when you do that, you get 19.0 joules per gram degrees Celsius. Okay. All right. So a couple more things to go over before we call it good for today is that, you know, this is chemistry. So what we really want to focus on is the energy change that are occurring in chemical reactions. And so we could use the same thing, the same setup, the coffee cup calorimeter, to determine if a reaction, first of all, is exothermic or endothermic, but then also we can use it to quantify the amount of energy that's being absorbed or released into the system. Okay?
Greetings and felicitations.
Okay, so let's say that we have this chemical reaction, which we learned about last week. This is an acid-base chemical reaction. So we know that this happens, called a neutralization reaction, produces a salt and water.
beer.
I don't really understand why I put that sound effect there, but I did. Anyway, so this is the initial conditions. We have 25 mils of HCl and it has a temperature of 18.5. And so then I come along and I mix in another 25 mils of sodium hydroxide, bringing the total volume to 50 mils, and it caused the temperature to go up to 25. It was at 18.5. When I mix the two together, it's at 25, okay? And so the question would be, well, what is the Q of the reaction? How much energy is transferred in this reaction, to or from this reaction? So the system is the reaction itself. And the surroundings would be the water that the reaction is taking place in, because remember, the water is just kind of it's a matrix for the reaction in which to occur. It's not really, this reaction happens to be producing water, but just an insignificant amount compared to the amount of water that was already present, because these guys were in solution. So if we are running a little short on time, so if you don't mind, I'm just going to scroll through this with the PowerPoint. So key is knowing where to start, and start with the law of conservation of energy, that whatever happens in the calorimeter, the Q of the calorimeter, is equal to the negative of the Q of the reaction. And this is what I'm solving for. I'm solving for Q of the reaction. But I know that MC delta T of the calorimeter can be calculated because I know the mass of the water, I know the specific heat of the water, and I know the change in temperature. Went from 18.5 up to 25. Okay, so the calorimeter, mass of the water, specific heat of water, delta T of the water. So the trickiest part about this calculation is understanding where the mass of the water comes from, the correct mass of water. So remember what I have here. I have 25 mils from one solution, and then I have 25 mils from the other solution. So I have a total of 50 mils of water, which means I have a total of 50 grams of water, okay? Total of 50 mils because I've combined the two solutions. And so that temperature change occurred in 50 mils. And since the density of water is just by definition, if these are solutions, these are dilute solutions, so we can assume that the density, well, actually it tells us, assume that the density is still 1 gram per mil. So it's 50 grams of water. So this is the mass that I'm going to use for the mass of the water. So 50 grams of the water times 4.184 times the difference in temperature, final minus initial, and you get 1360 joules, okay? And so to answer the question, it's just the negative of that Q of the calorimeter, right? So it's the Q of the reaction is negative 1360 joules. And again, that should make sense. This reaction is an exothermic reaction, so it should have a negative value. It's releasing, the reaction is releasing energy into the surroundings. And so that's why the temperature of the water went up. That's why it went up to 25 degrees Celsius, because it absorbed all that energy that's being released by the reaction of sodium hydroxide with hydrochloric acid. Okay? All right, so strictly speaking, that's the answer to this question, but we're gonna fiddle with this number in just a couple minutes here. Okay, and that's what these, what I've labeled here as housekeeping items. So we saw in several examples today that energies are typically fairly large numbers, and so often what we will do is represent the energy in units of kilojoules rather than joules. So you just have to be aware of that, and anytime you have like a difference where one part of the calculation might involve joules and another part of the calculation might involve kilojoules, you have to reconcile that. You either have to change them both to joules or change them both to kilojoules.
Oh, indeedly doodly.
All right, and so the other thing that we're going to see is that often we will express these energy changes in units of kilojoules per mole. So that's what we're going to do next, is we're going to do the per mole part. So we learned from our calculation above that it was a certain number of kilojoules. Well, that was due to a certain number of moles of HCl. So how many moles of HCl? You just pick a reactant. If it doesn't specify, you just pick a reactant. In this case, one of the reactants was HCl, and I had 25 mils of it. So 25 mils, first of all, convert that into liters. So there's 1 liter of the HCl solution, we have 1,000 milliliters of the HCl solution. And it was a 1 molar HCl solution. So 1 mole per liter. It won't always be 1 molar. Just in this particular problem that we just did, the concentration was 1 molar, 1 mole per liter. So again, milliliters will cancel, liters will cancel, and so I have units of moles of HCl. So now I'm going to take that amount of energy that I figured out in the example problem, negative 1360, and I'm going to divide that by the number of moles that I just did calculate, 0.025 moles, and you get you know, the negative 54400 joules per mole. But again, let's just change that to kilojoules to make it a smaller number. Move the decimal place over 3 places, 1, 2, 3, and you get a negative 54.4 kilojoules per mole. Okay, so that's just to show you what I mean by, you know, the typical units we're going to express these energy changes for reactions in. The energy change for chemical reactions will usually have units of kilojoules per mole.